Hopefully this won't take the whole class time, and you can get out early. So just a reminder, like everyone on board, you guys will have class on Friday, Dr. Cody will be back on Monday. My name's Sarah, this is Alicia. We're two of his grad students, and he asked us to come in and go over some characterization stuff today. He may go back over and review it again when he gets back. But ideally he wants to like move on with his lectures. Oh no. Alright, we'll deal with it later. I don't know, nobody knows how to turn those off, do we?
I mean, you just cover with like a sheet of paper.
What'd you do?
I just hit blank.
Oh. I tried that. Okay, so just give me a quick thing. What have you guys talked about powder characterization at all in this course? I don't know, not at all?
We talked about the sizing, and that was the last thing we talked
Like
about.
particle size distribution stuff?
More like how do they differentiate sizes, like sizing.
Okay. What is the title of this course?
Processing.
Processing, perfect, okay. So you guys are learning about processing principles. Great, good to know. So basically what we're gonna talk about is how we characterize powders. Ideally, we're gonna do this like before we use it in some process. So you get a powder in from raw batch components and you wanna figure out different aspects about it so that you can figure out how it's gonna behave when you actually make something from it. So things that we look at, density, specific surface area, particle size, and then the size distribution if you have more than one range of sizes in your powder. Have you guys done any powder packing calculations yet? At all? You will get to that, I guarantee. We've done a lot of that in 203, so some of you guys should be familiar with it. Thermal analysis, chemical analysis, stuff like that, that's going to give you what your chemical makeup is. So we use things like inertial coupled plasma and wave dispersive spectroscopy. And then thermal analysis, which is what a lot of Alicia and also Heidi have been doing in the thermal lab. This isn't the one where the lab's attached to the course, right?
No.
Can they potentially take that lab still?
Yes,
Yeah.
it's in the block of this semester.
Cool, okay. So if you guys are interested in like thermal analysis properties of materials, so like glass transition temperatures, combustion temperatures, things
Thermal
like that.
expansion,
Coefficient thermal
centering
expansion.
temperatures.
Yeah, centering temperatures, stuff like that. You guys can sign up for that lab still, maybe, I don't even know
Yes.
for sure.
Yeah.
I think there's still open spots. But today, ideally, we're gonna talk about density and specific surface area, because that's what Dr. Curdy asked me to talk about, and then he's gonna move on to some of these other methods and things that we look at when he gets back next week. So, let's see what we got. All right, so have you guys heard of a helium pictometer before? I know the 203 kids have, we did a lot with that. Basically, there's a couple of different pictometers that we can use. You guys understand what density is, right? The whole mass divided by volume aspect from like physics or whatever in high school. Familiar? Cool. All right, so all of these methods that we're going to look at essentially play off of this relationship here to estimate the density of our different materials. One of the common ones we use is called a pictometer cup, right? Pictometer bottle. I just brought this in as an example. But basically this is a cylinder or a container of known volume, and what you do is you put your powder or liquid in here, it can be whatever you want to measure, and there's a tiny little hole on the top here. So ideally you would fill it up with as much material as possible, and then you essentially close this and like wipe off the top to the point where you can't fit any more mass in here, whatever you're measuring, and then you weigh this. And then you subtract the weight of your container here, and then so you have the mass over a known volume, and that gives you an estimate of the density of whatever you're measuring. You guys can look at that or pass it around if you want. Another way that we can measure density is called by the Archimedes method. Have you guys heard of this before? I'm going to try and spell Archimedes. I think I did it right. Cool. Have you guys seen this before? Basically, this is off of, I think it was a king that put his glass crown in a bathtub of water and noticed that the water level moved up in the bathtub whenever he put it in there. What? A philosopher. Was he looking at a king's crown to see if it was real gold? Was the story? Yeah. So he was trying to determine whether the crown was real gold or not, and then based on the water, the amount of water that was displaced was how you could estimate the densities. This is the same aspect of like when you get in the bathtub and the water level rises. So we have a specific method that we can do to estimate the density of materials with this. The issue with the Archimedes method here is that it measures what we call the bulk density of your material. And do you guys know the differences between different types of densities? Basically, you can have a bulk density and then a skeletal density or a true density. I know your homework questions I just saw had questions about that. A bulk density is, let's say you have some kind of ceramic compact that you've sintered, and it's not fully sintered, so it's not 100% dense. So you have open and closed pores. So an open pore is going to be whenever part of the pore can be open to the surface or air getting in there. And then closed pores are when the pores are completely closed off from the outside of your material. This looks like Swiss cheese, but I think you get the gist. So these are called open pores. I don't know if you can read that. And then the ones that are closed, obviously, are called closed pores. So with the Archimedes method, ideally, it's going to measure your bulk density, and your bulk density takes into account your open pores, because when you put your sample into water, or whatever, you can use kerosene too for things that are unfired, your water is going to penetrate in the open pores here, but it won't go into the closed pores. So you get a density measurement that includes the volume with your displacement of these closed pores. Okay? So with your bulk density, do you think the density value that you would get would be higher or lower than what the true density would be if you didn't have any of these closed pores? What do you guys think? Lower, because you're going to have a higher volume measurement with your displacement, right? Over the same amount of mass. So how do we fix this if we have closed pores in our system? And we want to know the density of specifically just the material in our sample. Any ideas?
Use a medium that is small enough that it can infiltrate into those pores.
Yeah. Any ideas?
You know, argon.
Yeah. Okay, so we can also use really small gas. And ideally, this is not always the case, but ideally the gas will penetrate into these pores, and then we'll get a more accurate estimate of our density, which is going to be what we call our skeletal density. Okay. And that's going to not include, so it excludes open and closed pores, ideally. So our skeletal density is what we actually measure with the helium picnometer with our helium gas, which we'll explain how that works in a minute. And that works with our ideal gas law, which we're going to go over, but you guys know. Gardner.
Too far because of the camera.
Nice one.
The arrow. I'm pretty sure it's for the camera. How are you selling?
All right. All right, so you guys remember the ideal gas law from chemistry, right?
Yeah.
The Gardner thing. In your homework, Dr. Purdy, I think, asks to differentiate the difference between true and skeletal density. I don't know. A lot of definitions have those two as being the same, so we'll have to ask him what the clarification is on that. And I think the true density is like the 100% ideal case. So like, lowercase. So if you had absolutely no porosity in your system that you're looking at, it's all just your solid material that you're measuring. That's going to be your true density. The picnometer, it measures a skeletal density. Oftentimes, whenever we have a sample like this, to try to eliminate as many of these closed pores as possible, we'll crush it first in order to get a more accurate skeletal density. And that's because even though the helium gas is supposed to penetrate all of the closed pores, it doesn't fully sometimes. So we'll often crush it into a fine powder to eliminate any of those closed pores before we measure it in the picnometer. So we'll have to clarify with him but I believe the skeletal and the true should be very close, but the true is in the case of like absolutely no closed pores influencing your density measurement. Any questions about that? Okay. Can we go to the next one? Okay, so this is just two diagrams of different helium technometers. So basically how it works is there's a reference volume here, and then there's a volume that you put your sample into, and you can, there's two different types, the way that two different companies have set up their expansion cells here, how they work. But essentially you know the volume of your sample chamber, and you know the volume of your reference expansion cell. And you take it, you do a calibration to make sure that you have accurate volumes for both of these at a certain pressure. And then you put your sample in here. And basically you pressurize the reference chamber, and then you open this valve in between, and it equilibrates the pressure across the two cells here. And what the machine does is it uses the difference in pressure to estimate the volume that your material is taking up in the cell here. Okay? So you ideally measure your mass of your system first. So the helium technometer, you weigh your sample, and then you run it in the actual picnometer. So what the picnometer actually gives you is a volume, not a mass. It's actually measuring volume based on the pressure differential across these two cells, okay? And then with your known mass that you weigh beforehand, it'll actually compute it. A lot of them compute it for you, but the older ones you used to have to calculate it yourself. But when you input your mass, it measures the volume, and then you get your density, okay? And key point is that the helium picnometer measures the skeletal density of your powder, okay? Any questions on that? You guys will actually get to see them, how they work at first one. But take the lab portion of it. Alright. Let's see. That should be it. On the homework, the extra credit one that's asking you about the equation. So this equation is essentially on the second to last page here. It's essentially taking this ideal gas law and saying that the two volumes, so like you know both of these volumes, and after you put your sample in, the total volume here is going to be your volume of gas plus the volume of your sample. And then I think the VE is like your expansion cell.
Yeah.
Okay. So I don't actually know if there is a difference of the two setups. I'm not sure.
The only difference is that with the quantiferone, the sample chamber is not in a direct line with the gas.
Yeah, but that shouldn't, it still will measure the pressure differential.
Yeah,
They might not be different. That might be a
They
trick
run off the
question.
same theory.
Yeah, that might be a trick question. He does that sometimes. Okay, so the question 18 here, why would the picnometer not be applicable for measuring density of a ceramic body after sintering? Can you guys answer that? Like of a full sintered ceramic body?
Is it gas been permeated in the core?
Yeah. So your closed pores, you're not going to have the gas fully infiltrate your closed porosity there. So it won't be as accurate. So what we often do, like I said, is if we have a sintered body and we want to know what the skeletal density is, we usually crush it up and then put it in the picnometer and measure the density. So your Archimedes method will give you a bulk density, including your closed pores, and then picnometer gives you a skeletal density, which ideally excludes open and closed pores. Okay? All right. What do we got next? Specific service area. Love this. Have you guys talked about the Pacific service area yet? Okay. I know 203 has. All right, so can anyone tell me the difference between regular surface area and specific surface area? 203. Anybody?
Specific surface area is the amount of total surface area for a bulk weight of powder.
Right. It's on a mass basis, so it's per gram. And normal surface area is like an extrinsic and intrinsic property,
It's
right?
like that specific, whatever particle you're looking at, it's the amount of surface area on that.
Yeah, the surface area is just only an area. So the example we usually use is like a basketball and a golf ball, and you're gonna make fun of my not knowledge of sports here. Is that kind of what a basketball looks like?
Yeah.
And then golf ball?
Wait, what?
Am I close?
Yeah.
Just use your imagination, okay? Here,
Yeah. Wait, don't think I'm
is that better? It's better, right?
So a line that goes around the horizontal thing of the basketball.
Sure.
Yeah, like that.
All right, I'm not majoring in art or sports, so just work with me. All right, so if I asked you just surface area, which one of these has more surface area?
The basketball.
The basketball, right? So this one has more surface area, because if we look at the size, like obviously it's gonna have more surface area than this little golf ball. So if we're looking on a per gram basis, so surface area is usually represented as meters squared per gram, whereas like surface area would just be meters squared. So if we're looking at a per gram basis, which size would have more specific or have a higher specific surface area? The golf ball. And that's because per gram, so like let's use relative number of balls. If we had 10 basketballs versus 10 golf balls, which one would have more surface area per same mass?
You have to use more of like a weight amount. You
Yeah,
can't
that's
just say-
not good. All right, if I had 10 kilograms of basketballs and 10 kilograms of golf balls, which would have more surface area per mass of material?
Golf.
It's gonna be our golf ball. That's maybe not the best explanation, but we'll wrap our heads around it in a minute. So, just key point to know that specific surface area is per mass, so per gram values. And essentially that means that if you have smaller particle size, you're gonna have higher specific surface area. And then the reverse is true as well. For larger particles, you're gonna have a lower specific surface area. That's kind of the key point. And that comes into play with things like sintering, dispersants, so any kind of surface chemistry stuff that we look at. So like the driving force for sintering is usually to reduce surface area, right? So you have more energetic sintering reaction if you have more surface area. So basically that means that our smaller particles are gonna densify faster and at lower temperatures than our larger particles because we have more surface area to react with each other of the particles with. Same things for whenever we look at rheology, like rheological properties. You guys are gonna do like viscosity, things like that. Whenever we put dispersants in the system, which are essentially things that react with the surface of your particles, you're gonna need more of it to react if you have more specific surface area in your powders than if you have a larger particle. Okay? So, the BET, the way this works, essentially we start the same way as with our picnometer, so we measure the weight first, so we weigh our sample. This is kind of hard without you guys seeing it, but basically you need a decent amount of surface area to be able to get an accurate specific surface area measurement. So like if you have a larger particle size, you'll need more sample in the BET tubes because they have lower specific surface area. And if you have smaller particles, you'll need less of it. So like things we do like nanoparticles, stuff like that, where you have like a couple hundred meters squared per gram of surface area, you usually need like a half a gram or less to get a surface area measurement. What we do is called degassing next. Essentially, if you have particles, even if they're dried, like in our drying ovens, we usually keep about 100 degrees Celsius, you'll still get water molecules that are adsorbed on the surface of your powder. Okay. Do you guys know the difference between adsorption and absorption? This is a big thing he normally drives home. Yeah, so adsorption is when you're dealing with things stuck on the surface, and then absorption is when it like takes it into the body of whatever you're talking about. Okay, so this is adsorption with a D. Okay, so we have water molecules that are still stuck on the surface of our powder, and we want to drive as many of these off as possible, because when we do our measurement for specific surface area, we're going to be condensing gas on the surface of our particles. So if there's extra water molecules on there, you'll get an inaccurate surface area measurement. So what we do is we drive nitrogen at elevated temperatures. So we usually do like 150 C, I think.
Yes.
So we drive nitrogen gas over the sample, and essentially that drives off any of these water molecules, ideally. Okay? So then we weigh our sample again to make sure that some of this water has been driven off and we haven't gained mass for any reason. So gas, weigh again. And then we can actually do our measurement. So how the measurement works for BET. All right, so we have our powder, and what we do is we pull a vacuum on the tube that our sample's in, and then we pump in nitrogen gas. So we have N2 coming in, and we're at liquid nitrogen temperature here. And this part is key. So we have N2 gas coming in our sample tube, and then we cool it to the temperature of liquid nitrogen. So if we have nitrogen gas and we cool it to liquid nitrogen temperature, what happens to the gas? Yeah, it condenses, right? And the nice thing about this method is that when it condenses on the surface of our powder of whatever we're measuring. So for 203 purposes, let's call this alumina. And we get N2 gas adsorption on the surface of our powder. So what the machine measures is when this gas adsorbs onto our powder, there's a pressure differential that occurs, and it measures the change in pressure and then uses our converter again to estimate the amount of gas, that like the mass of gas, essentially, it's number of moles, but like the mass of gas that's adsorbing onto our surface. And then what it does is it estimates the area that half of a nitrogen molecule essentially is going to take up on our powder surface to try and estimate the surface area of our particle. Does that, anyone have questions about that? Make general sense? All right, so the key thing about the BET that Dr. Carty always stresses is that this method corrects for multi-layer coverage on this powder. So that's kind of like a thing that always shows up on some of his exams and homework questions. So let's say that you have molecules that are not perfectly spaced on here and you still have some open surface. What ends up happening is that you're going to get nitrogen molecules that might not be stacked, like might not be stacked exactly on a one layer thing. So the BET method corrects for this, which is nice. And with the BET method, it also doesn't matter what shape your particle is. So a lot of the different things you're going to talk about, like how we measure particle size distribution, they all assume spherical particles. But this method, it doesn't matter at all, because it doesn't matter if you have like a wonky whatever shape, like your molecules are still going to adsorb on a surface here, no matter what. So this doesn't matter what shape your particle is. Surface area by mass. So it measures your surface area, so it'll measure your, your square meters of gas essentially of the area, and then you put in the mass, and then that calculates your specific surface area for you. Okay? So we're on the pictures of those. All right, so like I was saying, the BET assumes multi-layer coverage, and it corrects for that. That's That's just like a key point he's probably gonna ask you about. I don't think you really need to worry about this. This is just looking at like the pressure differential that happens whenever you pump the gas in. It's not really, I can't see him ever blowing up again. But
You
it
know,
is.
ask it on the test.
I don't know, maybe.
Like, you might ask, what does the BET assume? And monolayer, multi-layer,
Yeah,
but it will say like, but it corrects the way.
yeah, that would be a little test question. Okay, so this is like a case study example he wanted us to go into. This is some kind of manufacturing process, but basically the key point is that they have huge silos that they pump in all of the raw materials for, and we're going to be looking at, I think it's flint and nepheline cyanide that they use. So this is Buffalo, China. It's made in Buffalo, China. But they're bringing in like 6 rail cars of material per week, which is a ton of material. And then their batch size is ginormous. So I think the key point he wanted to talk about is like how we use powder characterization to kind of fix problems for like a real large scale thing. Basically what happened was somebody, when they, what?
I was saying
Oh, yeah. When they brought in one of these rail cars of material, somebody put the wrong rail car into one of these silos, so that they dumped about 51,000 pounds of the wrong material in a silo that should have had flint in it, which if you can imagine, like that's a silo that's stories high. That's like a huge mess up on somebody's part. And what they were worried about was that they were going to have to scrap the material in that silo completely. Has he talked about this before? No. And basically they called our group in here to try and figure out if they could still reclaim some of that, and if we could use any of like our powder characterization knowledge to figure out how to, save any of this material.
it costs about $300,000 just to get the silo vacuumed out. So like, they didn't wanna lose that and all the cost of the material and the cost of getting rid of the material, because you can't just throw this material in the, like, you have to get rid of it.
So one of the other issues with the silo is how the material flows through it. So if you have materials of different densities, what happens is normally you'll have material kind of get bulked up here on the sides and the stuff from the top will flow through. So they were worried about it mixing essentially the stuff that was dumped in incorrectly coming out and then leaving all the rest of this stuff. So it was kind of a mess. Does anyone have any ideas of like how this might have been fixed?
Ultrasonication or something along those lines.
Of a silo?
I don't know, you could just use something that puts some sort of vibrational energy and would knock stuff off the side.
Okay. Got it. So how do you tell like when all of the other powder's out of the silo? Or are you just saying like knock it all out, like clean it?
Like clean it out, yeah.
Okay. Basically, I think the way they first looked at it here, they were trying to look at the difference in densities to see if, like, how I just showed with that different flow properties, if, like, one of the materials would flow out first over the other ones. You guys are going to go into so much depth with mixtures. It's going to be a double, triple review for 203 again. We're going to go into it a little bit today. Sorry, but it's important. But basically what they found is that the densities of the two materials were almost exactly the same. So you couldn't actually use like the flow properties for different densities for materials. So their possible solution that Dr. Carty's group proposed, anyone take a hint at what it deals with? We just did an intro to it.
Using BET to determine what your
Specific surface area, yeah, good answer. Okay. So what they did instead were they looked at the specific surface area of the two materials, and even though the densities are so similar, they were able to use the specific surface areas to differentiate how much of each was in whatever they were doing. And basically this is going to look at the role of mixtures, but they looked at historical data from the past. So this is specific surface area of the flint, which you can see kind of averages out about 1 there. And then the nepheline cyanide is kind of all over the place, but essentially around 2.5-ish for the average specific surface area. So what they were looking at then is how the surface area was changing as they pulled material out of the silo. So this was certain batch number. So you can see when they added more nepheline cyanide in, because it has a higher specific surface area, the average specific surface area of what they were measuring jumped up. And then as they went through and used more and more of that material and pulled it out, that slowly started to lower. And basically they were able to track how much of each material was in what was coming out of the silo to the point where it went back to being completely flint. I don't know what flint looks like. I think they're very similar in like color too, is also why they couldn't tell just like visually what was going on. Anyway, the reason that this example is important is because it brings into account something that is called the rule of mixtures, which is essentially like a proportionality relationship between different physical properties of powders. We're going to do an example today that's dealing with specific surface area, but you're also going to end up doing a density calculation probably several times with the rule of mixtures. So basically, you can either have it be on a mass basis or a density or a surface area basis, right? Volume basis. Mass basis or volume basis. Specific surface area is on a mass basis. Okay, so the key thing here is that specific surface area is on a mass basis. And this will 100% be on a test question at some point. And density is going to be on a volume basis. Easy way to remember that is specific surface area is measured in meters squared per gram. So this per gram here, that's mass basis. And then our volume is we do a volume per gram. So typically for density, it's cubic centimeters per gram for density, right? Grams per cubic centimeters. Nope, I was like, that's not right. Sorry, erase that. It's grams per cubic centimeters, so per volume. So that is on a volume basis then. Okay? So the way that the rule of mixtures works is you essentially, for the mass basis, have a mass fraction of whatever your component A is, times your specific surface area of your component A. So specific surface area of A, and then you have a mass fraction of component B times your specific surface area of component B. And this can go on, even if you don't have only two components in a system, you can have as many components as you need. But typically the nice thing about two component systems is that we can solve this just knowing the total specific surface area and the component specific surface area. So our mass fractions times our specific surface area of our individual components is going to be our specific surface area total, which is in this example what we're measuring at the bottom of the silo when we pull a sample out. So by just knowing what the specific surface area is of whatever we're pulling out of the silo, we're able to calculate our mass fractions of our two components, which are going to be flint and nepheline cyanide. Okay, so what we're going to do is just a quick exercise to give you guys an intro to rule of mixtures. So we're going to use this point that's circled here. So let's say that you guys take a sample from the bottom of the silo and your specific surface area is like 2.2 meters squared per gram. Okay, so this is your total here. We're saying it's 2.2 meters squared per gram. So do you guys want to work together by yourself? I don't really care, but take a couple minutes and try and figure out, we're solving for the mass fraction for our flint and then our mass fraction for our nepheline cyanide. And then your specific surface areas of the two are going to be R1 here for the flint and then 2.57 for your nepheline cyanide. Okay? Take a couple minutes to try and figure that out. Key point with the two mass fractions. So if you only have two components and you're taking a mass fraction of them, what does the total have to add up to of our two components then?
1.
1, right. So you have to use that relationship as well in this.
And no matter how many components you have, it would equal one, like all the fractions would equal one. All of this, all of these questions together, like if you can answer just one, it's 6, 7, 8, 9, they're all the same. Most of that one's just what they did for how they got there.
Yes.
Yeah, I don't know, it's just like 14 matches, 8 days. They found the addiction was only 50. They found the truck was 51,000 pounds, and they dumped almost 3,000 pounds worth of material.
Anybody have any questions?
Help. Everyone else?
What's the answer?
I'm gonna tell you that.
How about you write it on the board?
Yeah, Dante, would you like to write it down on your board? Thanks for volunteering.
Okay, I'm not there yet.
Oh, I missed you.
Did you really?
No.
Wow.
That's exactly where I got stuck.
Oh, it's not. Sidewalk chalk doesn't erase it. So somebody thought it was chalk, but it's super strong chalk. So
Because this is really
it's every
Alright, did anybody get answers? I guess, yeah.
I got 24% A and 76% B.
Of Flint, right?
Oh, yeah.
It's like 23 something.
Should we have someone write on the board the steps they went through?
Yeah, if someone wants to, they can fill it out.
I mean,
You want to? Here, have it. Get that. Did anybody get anything goofy or different than that they don't understand? Okay, so write it out.
It's okay if you don't understand what's going on.
Dr. Cardi is going to go over several more roll mixtures examples. Do I need to write this bigger? Did everyone see this?
Write it a little bit bigger just for the camera. Just because the camera's super.
Fair. And then Dr. Cardi will also, I'm not going to do it today, but there's also a way that you can convert between the two of a mass and volume basis. So if you have specific surface area and you want a volume fraction of whatever components you're looking at, you can take the inverse, but we'll show you how to do it, essentially to do it on a volume basis as well. So essentially what you're doing here is you're taking, like, you're solving a system of two equations. So you have your rolled mixtures equation here, and then your relationship between your total mass fractions. Can anyone explain why there's a problem that comes up if we have more than 2 components with our rule of mixtures?
Then you have 2 unknowns.
Exactly, so we have 2 unknowns and only 2 equations, so we would essentially need another equation in order to solve a 3-component system.
Three
3 unknowns?
unknowns. For like a 3-component system, three
Right,
unknowns,
3 unknowns, yeah.
then you would need 3 equations.
Because you can set up with that relationship to have it be 2 unknowns with a 1
Yeah,
thing.
okay.
But you would need another equation. So there's other things we can do that Dr. Carty will probably go over, but you can also measure things like coefficient of thermal expansion with a rule of mixtures aspect here. So that'll essentially, if you can also measure coefficient of thermal expansion, that'll give you another equation set up with a proportionality relationship that you can essentially solve for a 3-component system. But just as a note that you can only solve 2-component systems like this if you only have specific surface area or your density for whatever you're looking at with rule of mixtures. Okay. Okay, so the diagram, all of this stuff here is basically showing that they were using rule of mixtures to calculate the percentage of flint that they had of the 2 components. And then using this, they were essentially able to monitor that within about 12 or 14 batches of pulling material out of the silo, that they essentially had almost back to fully flint for their materials. And that essentially all of the incorrectly dumped nepheline cyanide had left. Okay, thanks, Abby. So, does anyone have any questions about this? Like I said, you're essentially taking 2 equations and plugging your unknowns in the first equation here, and then using that to solve through for one of your components, and then you just use 1 minus that to get your other component. Do you guys have any questions about that? You're going to see that several more times. I'm sure you'll have homework on it. Okay, so this is just the last slide we want us to get through. Essentially, they were able to solve the problem within about 8 days, and they didn't have to drop that $300,000 to clean out the entire silo. So just looking at simple things like powder properties can really help us industrially in what we're doing with our large-scale powders. Any questions on anything we talked about today? Okay. Do you guys have, just while we're here, we got like 10 more minutes, any questions on the homework? I guess either the ones you're working on now, but specifically the characterization, that's homework 3, we can be moderately helpful. Do you guys have questions when you look at it?
I haven't looked at it. You're not meeting.
You know where our office is?
Yeah. They can't stop us.
I was gonna say, I can't stop you from walking into the office, but like, I can put my headphones in and try to ignore you. But we can try to help, obviously. But now would be an even better time if you had questions since I'm here. Yes, but if you looked at it, I can help you now.
The issue we learned in 203 is that you don't know the material that's on the homework until like the day before it's due.
Yeah, that's not gonna change. We talked about some of this, like the deriving equation. Okay, so the deriving equation for specific surface area versus particle size with the density, you guys can kind of, you guys can,
know that.
yeah, you can goof on that without him talking about it.
There's some easily Googleable things.
Yeah.
Also, if any of you took 203, obviously know most of this.
Yeah, some of this is a little bit.
Some of it's new.
There's a
Yeah.
couple of things like
Here, this is 11 and 12 is all rule of mixtures. You can start on that now. 13 the density stuff. You can work on the picnometer stuff. Yeah, you can start it. Yeah.